Your test is this coming Wednesday. Be here on time, bring a pencil, and know your student number. The format is just like the sample test, 50 multiple choice questions on material that we covered here. I won't be asking anything that we haven't discussed in the class so far, including today's lecture. Okay, so we talked last time about neutron stars. Basically, they are formed when the collapsed core doesn't have too much mass. If the mass is less than about 3 solar masses, then the collapsed core will form a neutron star, which is supported by the pressure created by degenerate neutrons. The density of neutron stars is enormous. It's about 10 to the 11 kilograms per centimeter cubed. It's equal to the density of nucleus, right? So there is a tremendous gravitational force that is trying to compress the star, and what is keeping it alive, so to speak, is the degeneracy pressure of the neutrons. But if the mass is too big, so that the Chandrasekhar limit for a degenerate object composed of neutrons is exceeded, the whole thing will collapse. The gravity eventually wins. Throughout the life of the star, the crushing force of gravity was always fought by either the pressure created via fusion reactions in the core or degeneracy pressure in the case of white dwarfs and neutron stars. But if the mass of the end object is too big, the gravity will win in the end. So, whoops. So if the mass of the collapsed core is greater than about 3 solar masses, the pressure exerted by degenerate neutrons cannot support this collapsed core, and eventually it collapses into a single point singularity. The resulting object is called black hole. So just to remind you of the concept that we talked about when we discussed Newtonian theory of gravity, the concept of escape velocity. I'll denote it with V escape from a body of mass m and radius r. You see, any mass will exert force of gravitational attraction on the bodies around it. So if I take this car key and toss it up with certain speed, it would climb up, it would slow down as it goes up because it's being pulled down by gravity. It will reach certain height that it depends on the initial speed, right? And then it will fall down. If I toss it up with a greater initial speed, it would climb a higher distance, but eventually it will stop and come down. And the escape velocity, by definition, is the velocity with which I have to project this so that it never returns. It basically, its speed stops when it is at infinite distance from us. Okay, so that's what escape velocity means. For instance, escape velocity from the Earth is about 11 kilometers per second. So if I want to launch something so it never comes back, I have to give it initial speed of at least 11 kilometers per second. It will take off and never come back. Okay, so if I have this object of mass m and radius r, it turns out that the escape speed squared is given as a product between gravitational constant, the mass of the body, over its radius. This particular result is obtained with Newtonian theory of gravity, and any a first-year physics student can actually get this result from the conservation of energy by saying that the kinetic energy of a moving body that is associated with its speed plus its gravitational potential energy is constant. It cannot change. Turns out that if you apply general theory of relativity, which basically is a correct theory of the gravity, that the result is essentially the same. There's just a different numerical prefactor here, but what we are interested in is how this escape velocity depends on the mass of the object and its radius. Okay? So if I have a given mass and somehow I compress it into smaller and smaller volume, I keep on decreasing the radius, the escape velocity will start increasing and could become greater than the speed of light. Okay? Then nothing, including light, can escape the gravitational confine of this body. Then nothing, including light, can escape the gravity of the body. If there was a source of light at a distance from this body, which is where in the region where the escape velocity is bigger than the speed of light, then that light could not leave. We could not receive that light. Hence, by definition, it would be black, right? Black body is something that does not produce photons of any wavelengths. So that's the reason why it's called the black hole. There is a distance called Schwarzschild radius. It's a distance from a body where the speed of light, the escape velocity is greater than the speed of light. Okay, so if this is the singularity, it's the point into which all of the mass of the collapsed core has fallen, so to speak, then there is a sphere around it with the radius equal to this Schwarzschild radius, so that no information, nothing can leave this volume of radius Rs, and the boundary around it is called event horizon. So we can't see any events, nothing beyond the event horizon. Nothing can leave this volume of radius Rs. Okay? And it turns out one can show that basically the value of the Schwarzschild radius is related to the mass, m, as 3 times the mass, where the units are such that then Rs is expressed in kilometers, and the mass in solar masses. Okay, so if I had a black hole or an object of the mass, say, 10 solar masses, then the corresponding Schwarzschild radius would be 30 kilometers. And the bigger the mass, the larger is the radius of the event horizon. Now, what observational evidence do we have that such objects, black holes, actually exist? Okay, the possibility that these objects exist was from the very beginning present in the Einstein's general theory of relativity that he put forward in about 1916. But the question is, are these just, if you will, figments of imagination, something that is theoretically possible but actually does not exist? And the answer is no, these things actually do exist in the universe. And let me explain how we actually can detect them in spite of them not emitting any light, being black, right? So typically what you have is a binary system consisting of a normal star and the black hole, and the two are bound together by the force of mutual gravitational attraction. And as those of you who took astronomy 1P01 will remember, when we have two bodies gravitationally bound to each other, they actually orbit around a point between them, so-called center of mass, that is closer to the more massive object. So both of them are actually revolving around this common center of mass. So then you see a star with invisible companion, and you know that it has the companion because you can see that the star is moving around this fixed point, the center of mass. Okay? Moreover, what happens is that the stellar wind particles get accelerated by the strong gravity of the black hole, and as they are being accelerated to great speeds, in the process they emit electromagnetic radiation, in particular X-rays. So the material from the star that is falling into a black hole will produce X-rays. So then, in order to detect them, one looks for a binary system of a normal star plus its invisible companion, which has a mass of at least 3 solar masses. And you can work out the mass by observing the orbit of the normal star and actually applying essentially the Newton's laws of motion and gravitation, in particular as formulated by the third Kepler's law as formulated by Newton, to work out that that companion that you can't see has a mass that is at least 3 solar masses. But it's also a very strong source of X-rays. Okay, so you look for binary systems where one mate is not visible, but you know it must be there from the way the visible companion is moving. It has to have a mass of at least 3 solar masses. Moreover, it has to be a fairly strong source of X-rays produced as I've outlined here. And the first observation was actually done in Canada by an astronomer named Tom Bolton in 1971 using a 1.9 meter reflector telescope in now defunct David Dunlap Observatory in Richmond Hill. Years ago, we used to take students who were taking astronomy. Of course, the numbers were less than they are now. We used to take them for a field trip to that observatory. We would rent a couple of buses and go for a day. But it's no longer possible because the observatory has been closed. Now, what he saw, the normal star, was star Cygnus, and the corresponding black hole was named Cygnus X1, right, as a source of X-rays, X, Cygnus X1. The mass of the star was found to be 27 solar masses, and the mass of the black hole 15 solar masses. That's nice big value. You see, if you get something that is close to the threshold of 3 solar masses, you're not quite sure. Maybe you have a binary system of a star and the neutron star. Okay? Because neutron stars are very dense, they have a strong gravity, they can also pull in the solar wind particles, which could then produce the X-rays, right? So if you get the mass of invisible companion near the threshold, you don't know. But when you get 15, which is way above the limit, the Chandrasekhar limit for objects supported by degenerate neutrons, they are fairly confident that that must be a black hole. You cannot have a neutron star with a mass of 15 solar masses. It's got to be a black hole. Now, as I said, in order to describe black holes, we need to use Einstein's general theory of relativity that is fairly complex. Advanced knowledge of math is required, and of course we cannot discuss it in any significant detail, but I'll try to convey to you the gist of it. I mean, what the theory is saying, okay? So to describe vicinity of black holes, but also very dense neutron stars, also very dense white dwarfs, and stars like our sun, one needs to use Einstein's general theory of relativity. I mean, he has two theories of relativity. One that he put forward in 1905, so-called special theory of relativity, that has to do with objects moving at a significant fraction of the speed of light. Turns out that our classical notion based on everyday experience of space and time as something totally separate are not actually quite correct. It turns out that if there was a spaceship moving at, say, 10% of the speed of light, and we could observe a clock inside that spaceship, that we would see, and before the spaceship was launched, the clock was synchronized with the one that was left behind on the Earth. It turns out that we would see that clock moving together with the spaceship at the speed of, say, 10% of the speed of light would run slower than our clock. It would fall behind. Also, the lengths shrink in the direction of motion, so on and so forth. So that was revolutionary. It changed our understanding of space and time, because before that, space was considered as an empty stage on which events take place. Okay? But it's much more subtle than that. Now, in his general theory of relativity, he actually extended his ideas from special theory of relativity in order to describe the force of gravity. One problem that he had with Newton's theory of gravity was that in Newtonian theory, the force of gravity is instantaneous force between two objects at a distance. And he could not stomach that, because one of the hallmarks of the special theory of relativity is that no interaction, no signal can propagate faster than the speed of light. There is nothing like infinite speed of propagation. Okay? So he was trying to reconcile the phenomenon of gravity with these ideas, and that's how, working for at least 10 years, he was able to formulate the general theory of relativity. And basic idea is that mass or energy bends space, and other objects move in that bent space along the paths of shortest distance, so-called geodesics. Okay, so let me illustrate this, okay, as shown here in this drawing. First of all, it is very hard for us, and it has to do with the way our brain evolved. You see, we are not moving, and things around us are not moving at speeds close to the speed of light, right? So we don't observe this mixing of space and time. And therefore, our brains have evolved that we react very quickly to the events happening in three-dimensional space. We have really hard time imagining spatial dimensions greater than 3. Just because we needed to process the information quickly in three-dimensional space. If there is a tiger jumping out of the bush to eat us, we had to react very quickly, either fight or flee, right? The basic instinct. So we can mathematically write down the equation for, say, 4-dimensional sphere, but we really cannot imagine it. On the other hand, we can understand things happening in dimensions lower than 3. Okay? So for instance, imagine here that the entire universe is in this two-dimensional sheet. Okay? So I have 3 objects of different masses, the smallest, the one medium size, and really massive one. And all of 3 of them bend the space. And the larger the mass, the bigger the bending. So if I had another object that was nearby, it would fall into this curved space. And that's basically how Einstein's general relativity treats the gravitational attraction. This big body bends the space-time around it, and then another body that I drew here moves in that bent space-time along the path of shortest distance, which is not going to be a straight line, but a curved path. Okay, so this is the gist of his general theory of relativity. And it turns out that our sun bends the starlight because it's massive enough. It has mass of 10 times 10 to the 30 kilograms, or about 300,000 times the mass of the Earth. And its mass will also curve the space-time around it. So does the Earth. But the Earth's mass is not big. The curving of space and time caused by the Earth's mass is not that great. It's hard to detect. Okay? However, sun is much more massive, and in principle, and that was one of the initial predictions of the general relativity, was that it should bend the starlight. As the starlight from a distant star passes near the sun, those rays will move in the curved space-time near the sun, right? And as a result, it would look to us that their light is coming from a different direction where they actually are. And let me illustrate that. Okay, so schematically this is illustrated on this drawing here. So here is the sun. Its mass will bend the space around it. Here is the Earth. And this is the actual position of a star. And as this starlight passes near the sun, it will have to move in the curved space, and eventually it would come to us in a direction seemingly going this way. So this here is the apparent position. And this bending, this angle here, Einstein predicted that it had to be 1.75 seconds of arc. Okay, and then indeed it was confirmed by Arthur Eddington, same Eddington responsible for mass-luminosity relation for the main sequence star, and the same Eddington who didn't believe Chandrasekhar, the young starting graduate student, about his proposal about the limiting mass. Of course, this can be observed only during the total solar eclipse, when the light coming from the sun is blocked by the moon. Otherwise, we are blinded by the sunlight and cannot see the stars that are behind the sun. So to see this, the moon has to be between the Earth and the sun. So we have here total solar eclipse. And Eddington went on 2 expeditions to the places in the world at that time, late 20s, to actually see this effect. And indeed, he was able to confirm Basically, you take the photograph of a night sky when the sun is not in the way, and then during the eclipse, you take the photograph of the same part of the sky, and then you compare the two photographs, two photographic plates, and you see that the given star has shifted, right? It apparently moved from here, where you saw it when the sun was not in the way, to here, right? And that amount of shift, the angular displacement of 1.75 seconds of arc, was exactly what general theory of relativity predicted. So it's not just something that exists on the paper, but actually these things could be observed.